Hey guys, welcome back to another video. So in this video, I'm going to be talking about Vsepr. So Vsepr, or valence shell electron pair repulsion theory, states for a formula, let's say AB4 or something. This formula could have multiple sort of orientations in space, and that's determined by how many electron lone pairs and bonds there are surrounding a central atom. Vsepr is basically governed by minimizing electron repulsions, which makes the structure more stable and more likely. So basically, knowing lone pairs and bonds around a central atom will help us know what the geometry is. Now, each geometry has a name, has a specific bond angle, and a specific polarity. And the way all this whole chart is situated is through something called steric number. Steric number is essentially the number of lone pairs and the number of bonds surrounding a central atom. Now, a quick disclaimer is, let's say you have something like this, that's a triple bond, and you're looking at the central atom. This still has a steric number of 2, regardless of the fact that this is a triple bond. This is just 1 in steric number terms. So one bonding region, another bonding region, so that's 2. So that's steric number. And knowing a structure's steric number will give us sort of where to start, and then looking at essentially how many lone pairs there are will help us get the actual geometry. Now, another disclaimer I'm going to talk about first is to not just base a geometry on a formula, because if you have a formula and you're not practiced enough, you're just going to assume it's something else, and you're not going to realize that there's a lone pair somewhere. So it's best to first draw the Lewis structure and then look at the number of lone pairs and the steric number. So let's do a few examples. So the first example I have is dihydrogen sulfide. Now, if we literally just match this up with what we have based on formula alone, we'll actually get an incorrect answer. That's why I'm always telling you to draw the Lewis structure first. So let's draw the Lewis structure for dihydrogen sulfide. See this? So we see 2 lone pairs here. That's really, really important. Okay, so now that we've drawn our Lewis structure, let's look at the steric number. So the steric number is the number of bonding regions plus the number of lone pairs. So there's 4 around sulfur. So we see that there is a steric number of 4. Now we see there are also 2 lone pairs, which means this is a bent or angular. This is a bent structure. If we went with formula alone, we would have probably gotten something like a linear thing, which is not true because there are lone pairs around the central atom. So now let's look at polarity. This indicates, because there are lone pairs here, that's a electron-rich region. It's drawing all the electrons here. So this is a polar molecule. Now, a good way I like to think about polar or non-polar molecules are all the basic geometry. All the basic geometries are non-polar. All the linear atoms are non-polar, and the square planar is nonpolar. The rest are all polar. That's just something you can keep in mind. So let's do another example. Our next example here is sulfur tetrafluoride. So again, another good starting point is to draw a Lewis structure. So let's do that. We're not done yet. There's a lone pair right here, which makes this molecule a lot trickier than it looks. So steric number 1, 2, 3, 4, 5. So steric number of 5. It has one lone pair, which makes this seesaw. And this is also a polar molecule. So essentially the hardest part about determining geometry is drawing the Lewis structures. That's why Lewis structures are so important as a foundation for bonding in general, because if we get the Lewis structure down, we just need to know some simple geometric rules and then we can just get it. So let's do one last example. So this is the last example, carbon dioxide. Uh-oh. Oops. Let's try the Lewis structure. And there are no lone pairs on the central atom. So what this tells us is this has a steric number of 2. Like regardless if these are double bonds, these are just treated as 2 bonding regions. So steric number of 2 just makes it here. And there are no other geometries. So it's actually just a linear molecule. And linear molecules are non-polar. Because if we look at it this way, the electrons are being drawn to the oxygens in similar amounts. So it kind of cancels each other out. So this is a non-polar molecule.